So, good morning, everyone. Again, myself Vishal P. Today, I'm going to speak about open GL functions, under which I have taken the topic of this topic. So, this is Bezier curves, and this is good morning, everyone. Myself Vishal. Today, I'm going to speak about computer graphics and visualization. Under computer graphics and visualization, my topic is OpenGL curve function. So, OpenGL curve functions. OpenGL, a widely used graphics API, does not provide built in curve functions. However, it offers several features and techniques that can be used to render curves effectively. Here are some commonly used methods for drawing curves in computer graphics using OpenGL: Bezier curves, NURBS curves, line segments, pixel based approaches, and shader programs. Let us see each one in detail. Bezier curves. Bezier curves are widely used in computer graphics to represent smooth curves. OpenGL supports rendering Bezier curves through approximation techniques. You can approximate a Bezier curve using line segments or evaluate it using recursive subdivision. By specifying control points and interpolating between them, you can create various types of curves, including quadratic and cubic Bezier curves. Here is a brief explanation of different types of Bezier curves. Linear Bezier curve. A linear Bezier curve is the simplest form, defined by two control points. It is a straight line segment that connects the two control points. Quadratic Bezier curve. A quadratic Bezier curve is defined by three control points. The curve starts at the first control point, ends at the third control point, and is influenced by the second control point, known as the handle or control handle. It forms a smooth curve that is typically used for simple curved graph shapes. Cubic Bezier curve. A cubic Bezier curve is defined by four control points similar to the quadratic curve. It starts at the first control point, ends at the fourth control point, and is influenced by the second and third control points. Cubic curves are more flexible and can create more complex curved shapes. Next one, we'll see about the NURBS curves. NURBS stands for non-uniform rational B-spines, and NURBS curves are a type of mathematical representation commonly used in computer graphics and computer-aided design CAD applications. NURBS provide a more powerful and flexible way to represent curves compared to Bezier curves. NURBS curves extend the concept of Bezier curves by introducing the additional control over the curve's shape, degree, and weighting. They are defined by a set of control points, not vector, degree, and weights. Here are some key characteristics of NURBS curves. Control points. NURBS curves are defined by a set of control points, just like Bezier curves. These control points determine the shape and position of the curve. Unlike Bezier curves, however, NURBS curves allow more control points to be involved in shaping the curve. Not vector. A not vector is a sequence of parameter values that determine the curve's behavior. The knot vector defines the position of the control points along the curve and affects the curve's interpolation and smoothness. The knot vector is typically non-decreasing and influences the continuity of the curve. Degree. The degree of a NURBS curve represents the order of the underlying B-spline basis functions used to calculate the curve. It determines the number of control points that influence a particular segment of the curve. Higher degree curves can provide more local control but may introduce more complexity. Line segments. In OpenGL, there is no direct built-in function for drawing curved lines or curves. However, you can approximate curves using the line segments by dividing the curve into smaller segments and rendering them using OpenGL's GL begin and GL vertex functions. Here is a general approach to rendering curves using line segments in OpenGL. Determine the resolution. Decide on the number of line segments you want to use to approximate the curve. The highest of the resolution, the smoother the resulting curve. Calculate the control points. Depending on the type of curve you want to draw, example Bezier curve, calculate the control points that define the curve. You may need to interpolate or generate these points based on the desired curve shape. Divide the curve. Divide the curve into smaller segments based on the resolution you decided upon. For example, if you want to choose 100 line segments, divide the curve into 100 equally spaced sections. Render the segments. Use GL underscore lines to begin drawing line segments. For each segment, specify the vertices using GL vertex 2F, GL vertex 3F. Depending on whether you are working in 2D or 3D space, connect the vertices of adjacent segments to create a continuous curve. End the drawing. After the drawing line segments, use GL end to finish the drawing process. Pixel based approaches. Pixel based approaches in OpenGL refers to techniques where curves are approximated or rasterized using individual pixels. These approaches allow for more accurate rendering of curves but may require additional computational resources. One common pixel based approach is used to algorithms such as midpoint algorithm or the Bressenham's line algorithm to rasterize a curve. These algorithms determine the color of each pixel along the curve and set their colors values accordingly. Shader programs. Shader programs, with the introduction of modern OpenGL versions, okay, you can use the shader programs, specifically geometry shaders or fragment shaders, to generate curves. By defining the curve's mathematical equation and evaluating it within the shader program, you can render smooth curves directly on the graphical GPU. Create and compile shaders. First, you need to create and compile the necessary shader programs. This typically involves creating a vertex shader, a geometry shader, and a fragment shader. The vertex shader processes each vertex. The geometry shader generates additional vertices of primitives, and the fragment shader handles per pixel operations. Define the curve representation. Determine how the curve will be, okay, represented within the shader program. This can be done through uniform variables, vertex attributes, or texture buffers. For example, you might pass control points or other parameters, uniform variables, to the shader program. Okay, shader programs. With the introduction, so it is continued. Generate curve geometry. If using a geometry shader, this is where you generate the actual geometry for the curve. Geometry shaders allow you to generate additional vertices based on input primitives, example points and lines. For curves, you can generate the necessary vertices directly in the geometry shader based on the control points or the other parameters. Evaluate the curve within the shader program. Evaluate the curve equation or algorithm to calculate the position of points along the curve. This can involve mathematical calculations or interpolation techniques depending on the type of curve representation. Render the curve. Finally, based on the evaluated position, okay, use the shader program to render the curve. This can involve drawing points, lines, or other primitives using OpenGL's drawing functions like GL draw arrays or GL draw elements. Thank you.